In this video, I would like to cover what I call a typical your 200-ton unit. Keep in mind that from ship to ship, they are different units, but the principles of operation are the same. I will share with you how the electrical system works, and you will have to adjust it to your own. However, as far as motor thermistors, pressure transducer, which is 5 of them, the liquid thermistors, which is 10 of them, flow meters, the PRV, the BGD, and the CWC valve adjustments and troubleshooting, refrigeration, high pressure switch, the 20 SSRs, and the overview of the 4 PCB modules. All of these will apply to the unit that you'll be working with. Before we continue, remember, if you find the material in this video too technical, please watch earlier videos where I cover basic electrical knowledge. Keep in mind that the first 28 videos are best understood if you follow their sequential order. Now, back to our video. Before we continue, let me remind you that the refrigerant inside this unit is heavier than air. If there is a leak, it will flood the space just like seawater floods the space. But the problem is you cannot see it and you start suffocating very fast. So if you had difficulty breathing, run, because you only got a few seconds of air. So it's very important that whenever you be working close to one of these units, ventilation be properly working. I will also add that refrigerant in high concentrations, when you breathe it, is toxic by itself. In very low concentrations, if it's exposed to a flame or something that will make it too hot, it becomes very toxic right away. And if you're close to where the leak is at, it will cause you frostbite. So if you ever hear the alarm of the halocarbon go off, take it seriously. Now, let's continue. So, as I done in other videos, first I start with theory of operation. As you already can tell, there's a motor over here, and then there's a centrifugal pump over here. And then on this side, we got a low pressure refrigerant gas. As the impeller starts to turn, well, it will just exhaust the refrigerant into this chamber over here, which is called the condenser. Now at this point on, the refrigerant, it is at a high pressure, but it's still a gas. So seawater comes over here through pipe or tubes. It comes in and it goes right back out through the same place that it came in. So that's what the tech manual will say, that it's 2 passes, and it will remove heat from that high pressure gas. And what it will cause is that the gas will liquefy and start filling the bottom of the condenser. Now, there are 2 orifices in opposite sides, and they will start allowing the liquid refrigerant to meter out into the evaporator. These things over here, they create a seal because, well, it's filled with fluid over here, and that is refrigerant fluid. So the high gas or the high pressure gas that is above it, it will never make it to the evaporator, and that is what we want. Anyway, as the refrigerant just meters it out into the evaporator, in the evaporator you got chill water over here that is coming in somewhat warm. It goes in into pipes or tubes, and it turns around and it goes right back out the same place. But now the outside of those tubes is where the liquid refrigerant starts touching it, and it flashes into a vapor, and it removes heat from the chill water. So the chill water, it leaves out colder, and then all of that gas gets piped all the way back into the compressor to be sucked into, and the cycle repeats itself. Now, very important, in my system, the output of the chill water is supposed to be 44 degrees. But my motor always runs at the same speed and it's always on. So if we would just let it be, what it will do is it will just put all that high pressure refrigerant over here, which it will be liquefied, and because of so much pressure over here, all the liquid will be pushed at a faster rate, and the pipes that contain the chill water will get so cold that the output over here will be less than 44 degrees. We don't want that. To regulate that, and once again, it's because my motor cannot change speeds, there is this pre-rotational vane valves that they can open and they can close. As they close more, they will restrict how much refrigerant gas can go into the compressor. And by doing that, if we can regulate the chill water output. So the pre-rotational vane valve, what it does is it regulates chill water. Also, when the system gets shut off, those valves close completely, and when they are completely closed, then there cannot be any backflow of the refrigerant that is over here at high pressure back into this side. Now, how do the pre-rotational vane valves look like? Well, they're actually more like, it's multiple of them, and there is this arm that when it moves, it causes all of these little round things to rotate, and the vanes themselves, they just turn to the side, and to close, they just go like this. Kind of something like out of a science fiction movie. So this valve over here is what this is, and I will be showing you later on how to do some adjustments on that. Now, that was the suction side of the compressor. The exit or discharge side of the compressor, you have what is called a variable geometric diffuser, which is a plate that opens and closes, and it limits how much output can come out of the compressor. It is needed there so that whenever there is too much output over here, it opens more. Whenever is not enough output, and it starts closing. And by doing that, it reduces the noise that comes out of the unit. Also, here to the side, we got these high gas bypass valves, and what they do is they take some of the gas that was over here at the high pressure, and it just bypasses it straight from the condenser into the evaporator. That is needed to be done only whenever it is light load operations. Lastly, I want to make you aware that there is a condenser valve, condenser water control valve, that it determines how much water will be going into the condenser. So here is the main schematic, and it is divided into a motor controller side, which controls the compressor, the auxiliary oil pump, and there is the electronic side, which includes all the sensors and the 4 electronic modules. That is the input and output module, the power module, the microprocessor, and finally the analog module. I will talk about all of them, but before that, I'll talk about some of the sensors. The first component that I would like to discuss is the SSR. Here is one side of the SSR, and here actually the command of the SSR. So an SSR, I covered this in a previous video, but a quick review. An SSR is a device where we can use a small 5-volt signal to control a larger AC like we do over here. We're trying to open this valve over here. The valve is already open, so therefore let's decide to close it. The microprocessor, which will always have 0 volts over here and 0 volts over here, but when it decides to open the valve, the microprocessor will put 5 volts in this point, and what it does is it will short this over here. Now, it wouldn't be normally, it would be a solid state short per se, and it will put 115 volts through here, through this switch over here, which must be closed, and this switch is already closed. The valve will start opening, and this will not open until the valve is fully open, and then obviously that one will close until the valve will be closed. By the way, the reason why I did that is because this is how it is drawn here on the main schematic, and I'll show you what I mean by that. So there is the SSR, there is the disconnect switch, and then there is a particular valve. This one happens to be the PRB valve. I will talk more about the valve later on in the video. Now, in the schematic, I only show you this part over here, but I didn't show you this part over here. The command, it is all the way out of the microprocessor module. So the microprocessor module, it commands all the 20 SSRs. Yeah, by the way, there is 20 SSRs on the whole AC. Okay, so if you want to know what they are, well, here they are. This one controls the open and the close of the PRB valve. The next one is the diffuser, open and close, and the next one is the CWCV valve, the high gas bypass. So if you have a problem opening, or one of the high gas bypass valves is not working, one place to consider looking is obviously the disconnect switch, the SSRs. Now with that, SSRs, they do have 4 connections, okay? And you cannot use a multimeter in ohms to check if the SSR closed, because it's a solid state component. The only way for you to check an SSR is to remove it and bench test it, like I show you in a video of SSRs. But instead of removing the SSR, what I will do is I'll get an energized sheet, I'll go to the valve, remove the valve, I put one pin with the multimeter into one, which happens to be a common, and then another one into the command that I think is not getting. Like, let's say they open, and then I will command the valve to open from the microprocessor screen module. And if you never get 115 volts between that point and this point, that means that, well, the SSR or the switch is just not doing its job. If you get 115 volts between this point and the valve wouldn't open in that case, then the problem is at the valve. Same thing for testing for the close command. You just simply put your multimeter between 1 and terminal 3 of the valve. Now the disconnect switches, there's 5 of them. 1, 2, 3, 4, and 5. On the bottom 4, they are just, I call them disconnect switches because really, if you put it in the manual, you are disconnecting the SSRs from the valve in this case, and you can actually go manually, physically open or close the valve. If you put it in auto, now you put in the SSRs in line with it. And the same is true for all the other 4 over here. Now, the 4th one over here, when you put it in auto, you're really disconnecting it. And when you put it in manual, you just put in voltage to it straight, and you energize in 3M. 3M is the contactor, in my case, that energizes the auxiliary pump. If I suspect that this auxiliary pump is not automatically coming on, the first thing that I'll do is I'll put it in manual, and then the pump comes on, and then I will investigate why it's automatically not coming on. When you put it in auto, since you are removing the power from it, now the only way for it to come on is if it's being fed from the microprocessor. This one is the input and output manual via relay K2. And moving on to the current transformers, is 5 of them. 3 of them, they provide direct input current or signal into the input and output module. And that's how you are able to display, or the system is able to display the current that is consuming at the moment. And then the other 2 current transformers are wired in series with the overloads so that they can provide direct protection to the motor controller. If the overloads they get too hot, then obviously these contacts over here, one of these 2 will open, whether it be 1 or 2, and it will de-energize IMX. IMX is in direct in series with 1M, which happens to be the motor controller or the bed compressor contacts. So that's how that protection happens. Now, all signals that go into the cars, they go through or majority of them, they go through what's called a bleed-through capacitor, and that's what the symbol is in there. So the signal that goes through it is not supposed to be grounded, it's supposed to go through it, and all the harmful high frequencies stay on the outside and they don't make it to damage our circuit cars. These circuit cars are very delicate, and even if you open the panel and you use your radio to talk to somebody in front of the circuit cars, you can fry them. That's how delicate they are. Now, these bleed-through capacitors, the problem is that sometimes they ground. I have a problem with this one over here, C58, it grounded out, and what happens is that the AC will randomly start by itself and then it will shut off by itself. Well, what was happening is that when the ground was over here, it was commanding IR to energize. IR is the direct, is the way how the microprocessor decides to start and stop the generator. Because if you follow the path over here, there is this K1 relay that when it closes, as long as either you had this switch in start or run, it will put power in IR, and IR, well, I'm going to show you over here, when it closes, it puts power to this line over here and energizes IMX, and IMX processes contacts, and that's how 1M and the whole thing energizes. So yes, K1 is the one that starts and stops the compressor from the circuit input and output module. Now moving into the motor protection module. Okay, so there is a relay built inside this module, and it has 5 thermistors that 3 of them are sensing each of the phases of the motor, and 2 are 1 per bearing, at least for my side. All of them have to be good. If one of them burn up, I'm gonna have to get a right size resistor and put it to jumper it to simulate that one is good to go. There is no way that you can in the field change the thermistor if a thermistor goes bad, and there is a PMS card for all these too. So as long as all of these inputs are right, this relay will be energized, and this set of contacts RY-1 will be energized, and that is required to provide an input. This input right here, and that's one of the requirements for the system to be able to start. So never neglect to check to ensure that this relay is closed whenever you're troubleshooting that your system it doesn't want to start. I will talk more about these valves over here, but right now I covered them so you have a just understanding of what when I refer to them in the circuit card. So this is the PRV valve, and then the next one is the diffuser. Notice that here on the schematic, the PRV valve has a potentiometer attached to it, but the diffuser valve doesn't have one, because the distance of whatever this valve causes to open or close in the diffuser is actually sensed via what is called a proximity sensor, and the proximity sensor is actually drawn over here. So this proximity sensor actually detects the diffuser distance. Okay, so I was told by the field technician that one care for the diffuser is that you cannot go with the righty tighty lefty loosey. He says that sometimes righty means open the diffuser, sometimes righty means close the diffuser. But what you do is you have somebody out there open it, and then you look at the display, and then you see if the percentage is increasing or decreasing, and that's how you can tell before you start calibrating this. So that is the diffuser actuator. The diffuser actuator and the PRV valve are of the same type, so this valve and this valve, they can be interswapped. It's just that the difference is that for the diffuser you wouldn't be using the built-in potentiometer, and with that there is a built-in potentiometer in the PRV and the CWC valve, and that's what that is. And this input over here, which you see, goes over here, and eventually it's gonna make it into the analog module, which I'll talk about later. And safe to say that the potentiometer, or whether it be a potentiometer or whether it be the distance is proximity switch, is to let you know the position in percentage, or whether if those valves are open or closed. Be patient with me, I'm about to start talking about the cards, but before that, one more component. This one happens to be built inside of the circuit card, and it is these opto-isolators. Okay, so in here we got AC signal coming in, it goes through well, you can see a full bridge rectifier, and then it gets put into one side over here. I'm gonna show you a bigger picture of this. And here it is. So like for example, this is the pressure switch. When the pressure switch closes, it's putting 115 volts into the bridge rectifier, and really what you're doing is energizing this LED. When the LED turns on, so you are optocoupling. That means you're using light to provide an input over here. There is always 5 volts over here, and this is normally open when there is no light, but as soon as the light turns on, and it's not light that you can see, this is a built-in chip, okay? And then when the LED turns on, the 5 volt signal goes into, and it becomes an input to a microprocessor. All the optocouplers are into the input and output module, but all of those signals are always collected and then taken into the microprocessor module, as you can see over here, and that's what all these lines are coming in from the input and output module. And now that I get to talk about the input and output module, I don't have much to talk about because I already explained a lot of the stuff, but let's just do a quick review. This circuit card, it receives the input from the current transformers. It receives the start and the run signal. If you notice, the start and run is pretty much the same signal, at the exception of this one over here. That's the start position, and all of the inputs are up to a couple. Additionally, this car starts your via K2 your oil pump, via K1 starts your compressor, and very important over here, this is the PRV valve. So the PRV valve, when the system is energized, or the circuit card is energized, the circuit card will command, not the circuit card, the other one, the microprocessor module will command the closed SSR so that this valve is closed. And then there is this switch over here that has to be closed so that the circuit card, this one over here, can verify that this valve is closed. That's one permissive to be able to start the AC. Now let's talk about the 3 oil heaters. It's 3 of them, and if you notice, when IR is de-energized, well, the compressor, we know that is off, but also it causes this contact over here to always keep number 3 heater energized. Number 1 and number 2 heater only comes on whenever this SSR is commanded shorted by the microprocessor. Now, it is important to keep the oil temperature above 40 degrees so that refrigerant does not mix with the oil. When that happens, the refrigerant loses the ability to lubricate the compressor. Now, I also want to share this statement over here that it says, within the last 24 hours, 20 of those hours, the oil has to be about 40 degrees before you start the AC. The only exception to the rule is that if the oil was recently replaced. And I almost forgot to talk about the high pressure switch. As you can see, it clearly provides a direct input to the input and output card, and also is a required input to be able to start the AC. The last thing that I'll tell you about this card is that this card gets all the voltages, 28 volts, 5 volts, and so on and so forth, from the microprocessor card. And it has a total of 8 relays, which 2 of them I talk about. The other ones, I didn't go much into detail because in my AC, they are disabled. Alright, so I did mention that the microprocessor module gives the voltages for the other, the input and output module to function, but this card itself, it gets all these voltages from the power supply module. This is the module that I want to talk about next. So this, all it does is, if you can see, it has a small built-in transformer, not built-in transformer, a transformer next to it with a fuse, and that, what it does, this card is, takes those voltages and it creates your plus 28 volts, your plus 5 volts, and your minus and plus DC 12 volts. Okay, and then it fits it to the microprocessor module, and this module distributes it to the other 2 modules to include the analog module. The microprocessor module, as you can see over here, it has all the it receives all the inputs from either the input module or the analog module. An analog module, it has 1 channel, means pretty much really 1 wire, okay, that it will get all the information that this circuit card over here collects, and this one is the brains. It does all the decision making, and based on whatever it decides, it will tell the input and output module to start the AC, because remember, the input and output module is the one that can start the AC via K1, or it will energize any of these associated SSRs to open and close valves as it desires. And those valves over there. The third circuit card that, or the last circuit card that we haven't talked about, is the analog module. Well, our last circuit card is the analog module, and this one over here collects a whole bunch of analog inputs. Well, the variable diffuser, a proximity switch, and also the potentiometers that are built into the PRV actuator and the CWC valve. Luckily, there is this junction box, JB2, which you can open and you can just look at the actual wire numbers. And what I mean by these numbers over here, and you can just really take readings, and you can read with your multimeter what output is coming in from those sensors. Other thing that you can do from here is the thermistors. actually variable resistors that are temperature sensors. Those are those RTs, 10 of them, and their resistance is going to be dependent on the temperature that they have, and you can actually read them with a ohm meter, so you can do a field test. I will show you what I mean by that in a moment. And you can also read the flow meter to one side. To the left side, and here I got what is called the pressure transducer, 5 of them. Unfortunately, you don't have a terminal board for you to read all these pressure transducer, but you can actually read them on the transducer themselves. I will show you what I mean by that later. So let's see how would you read these guys over here. So as a demonstration, I guess here, RT1, you can put your multimeter in ohms, and based on the temperature that this one is, you can know if the sensor is reading right or wrong. Your tech manual will have something like this, a chart, okay? And at 32 degrees Fahrenheit, it's supposed to have a resistance of 9,795 ohms, plus or minus 98, and you can keep changing as the frequency, as the temperature changes. At 77, it will be this much. So that will give you a good high, a good medium, and a good low. And it is listed for all 10 of them, as you can see over there. So I like that because you can do, you don't even have to take it from the system to test it, although it would be best for you to take it out to the system and then have the gauge calibration guys put it in their temperature machine so that you can actually verify that they are working right. I did mention that you can read the flow meter. Now for the flow meter, you will have to go into that terminal box TV2 and then remove, see this wire, it's supposed to be connected over here. You need to actually have to disconnect it, hook it up into your multimeter to read milliamps, and then pretty much put your multimeter in series. And then when your system is running, all the readings that will come in through here, they will go through your multimeter, and you will be able to see the voltage over here change, and it's going to be anywhere between 4 to 20 milliamps, representing 4 the lowest flow and 20 the highest flow of the flow meter. That is an field check that you can do. Obviously all of these readings is supposed to be shown in the screen display of the AC, but let's say that it wasn't showing over there and you want to check your flow meter to make sure that it works with the multimeter, you could do that. Now, a moment ago I told you that the thermistors, they gotta have certain resistance, but what happens if a thermistor shorts or a cable to a thermistor shorts? That will create a short condition. Okay, so the analog module is always putting 28 volts to all of them. The analog module will disconnect power to not just that one thermistor, but all of them, and you will have to troubleshoot this and do the short, and then after that you're gonna have to go and press the transducer reset button so that all the transducers start working back again. And this button is located on the circuit card of the analog module. The analog module is located under the microprocessor module. To check if a transducer, a pressure transducer that is, if it's working, you have this chart over here, okay, the pressure transducer tolerances, and based on whatever pressure that it is, you should have a current going through it. So for you to check the transducer, the pressure transducer, those you have to do with power on, and really it's a small voltage, only 28 volts. And you go out there and stick your multimeter. It has to be a true RMS multimeter, and you stick both multimeter leads in here, and you should get the 28 volts as it tells you on the procedure. Then after that, you leave the multimeter in there. You don't touch it, you don't remove it, and you switch the multimeter to current setting and then you start reading, obviously, milliamps. You're gonna have to switch your multimeter lead from voltage to current, and you should be able to get the values of current that are according to this pressure over here. So anywhere with 20 psi for the chill water inlet pressure transducer, you should get a current somewhere in this range, and then as the pressure starts increasing, you should extrapolate and be able to determine what should be the one in between. So let's do an extrapolation example. So at 20 is supposed to be 5.6, at 180 is supposed to be 18.4. So what should be at 120 psi? Well, I take these two numbers and these two numbers, and I did some calculations right now. 180 minus 20, which is the psi, I got a difference of 120, and the current, I got 18.4 minus 5.6, and I got a difference of 12.8 milliamps. Okay, so we take this and that one, and we divide it the way it is. So the milliamps divided by the difference in psi, and we got 1.06, which is what it should change for each psi. So we want to find out what is 80. Oh, I'm sorry, 100. So 100. What's the difference between 120? It's 80. So 100 minus 20 is 80. So therefore, the 80, which is the difference, multiplied by 1.6, which is there's got to be a 1 over here. Sorry, I just didn't copy it right. 1.6. It give me 8.48. Okay, now we had to add that to the starting value, because this is not a 0. This is actually a 5.6. This is your starting value. So 5.6 plus, the difference, 8.8, it gives 14.08 amps, or milliamps, should I say. So when it is 100 psi, and here it should be 14.08 milliamps. I want to bring to your attention the flow meter. At the end of the book, it has what is called a flow meter troubleshooting guide, and it allows you to correct whether it's reading inaccurate, but also has steps that you can follow if in case it is reading out of range in the low side or in the high side, which is a different page. I wanted to show you a picture of the motor protecting module, but then recently I found out that my ship does not have one of them. And this is the motor over here, this is the pecker head, and that's where the motor protection module will be located in this type of ACs. And other ACs that I worked with in the past in other ships, they had it. So that's why I talk about it. Like G.I. Joe says, knowing is half of the battle. Well, I came across this page over here which talks about JB1 and JB2, and it is great because it is a quick reference to let you know what is connected. Like we can see the current transformers, the motor protection module, and over here some of the SV valves. I think 3 and 4 is the high gas bypass valve, and then obviously the PRV commands, and it looks like this one over here has the PRV sensors. Well, actually I talked about this earlier, but yeah, just make sure that if you ever need to troubleshoot and you're wondering where something is connected, you can find this page on your book.
Flow meter.
The flow meter.
It calculates tonnage. It tells you how much water flow you got going through the evaporator.
Okay.
Okay, here. Let me sign real quick.
Right, RT1, chill water inlet.
Chill water inlet, RT1.
Thermistor. RT2, chill water outlet.
RT2. Inlet, outlet, got it.
RT6, discharge temp.
Discharge temp for the compressor.
Compressor, yeah.
Okay, and that's the compressor right there.
Right, RT5 is here.
RT5, where?
Right there. That's suction temp.
Okay, that's RT5.
Compressor suction temp.
That's compressor suction temperature.
Right there. Right. RT10 is bearing temp.
Bearing temp. Temperature what? Or the
All bearing, all temperature of the bearings.
bearing temperature. Okay.
Right. RT7 is oil sump temp.
Oil sump temp over there.
That's RT7.
Okay. Next to the oil indicators.
Okay, down here. That guy, that's RT8. Right there.
That thing.
That is evaporator temp, RT8.
RT8 evaporator temp. Evaporator temp.
Okay, this one here, RT4 seawater outlet.
RT4 seawater outlet.
RT3, which is seawater inlets on the back side here.
Okay. It's called
RT3.
RT3 is the seawater
Seawater inlet.
which is behind, which we cannot see right now. Okay.
Right, and then you got RT9.
RT9.
Is condenser liquid temp.
Condenser liquid temp.
Okay, that covers your 10 thermistors.
It's 10 thermistors, okay?
Right, they all go.
So here we got a 200-ton yaw compressor, and as you can see, this is the motor, and here is the pecker head. You got alpha, bravo, and phase coming in to give power to the windings. I want to draw attention to these black boxes. If you will, well, they are current transformers. And transformers because this over here, a lot of current is going through it. I know it's a single core, single wire, but it still acts as a primary. And then there is a coil that is winding inside that black circle. And these are the two ends of that winding. So that will be our secondary. Now, obviously, this is the secondary for alpha phase, secondary for bravo phase, and so forth. These are connected in Y, and there will be, so this will be Charlie, this will be the output for bravo, this will be the output for alpha. There will be to a multi-tree conductor or multi-tree cable that it will feed to the computer. And they provide feedback of the current that is going to the motor. So if anytime you have issues with current not reading right, these guys, they need to be working and doing what they're supposed to be doing.